introduction to the definite integral. I'm your host, Dr. D. Okay, time to get going here. We've been talking about this last section, that the area under a curve can be measured by the definite integral. So here's our notation. The exact area between f of x and the x-axis is the integral from a to b of f of x dx. The integral from a to b of f of x dx. Now, this integral from a to b of f of x dx equals all of the areas of the infinitesimally small rectangles from a to b. So what we have is the limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I delta x. So what this is saying is we've got rectangles I equals 1, I equals 2, I equals 3, I equals 4, 5, 6, 7, 8, 9, 10, up to n. And we're letting n approach infinity, so we have infinitely many of these rectangles. How tall are each rectangle? The height is f of x sub 1, f of x sub 2, f of x sub 3, up to f of x sub n. The width is always delta x. Now, the notation that we have, this integral sign is really an s. And what it's saying is we're summing up all the areas. And the delta x is a width of each rectangle. Well, just like we've got slope is delta y over delta x, and when we want to make it infinitesimally small, it's dy over dx. So now we've made the delta x thickness of each rectangle dx infinitesimally small. So this is our notation. These are called Riemann sums, and the integral is the sum of all these rectangles. So let's cruise on. One more idea that we need before we get started is the concept of negative and positive area. If the curve f of x is above the x-axis, then the area is going to be the curve minus the x-axis, which is going to make it a positive value. But if the curve goes below the x-axis, then the area is going to be the x-axis minus the curve, which is going to make this area negative. Now, if I were to go from 0 to 1, that means I start at 0 and I move to 1, to x equals 1. That's going to be this first red area. And let's just say hypothetically that that area equals 1. Now, when I take the integral from 1 to 2, that means I'm starting at 1 and ending at 2, then that's going to be a negative 1. And once again, I just assigned those values at random, but it is negative. Then the area from 2 to 3 is hypothetically another positive 1. So if I were to take the integral from 0 to 3, then that would be the positive 1 plus the negative 1 plus the positive 1, which would end up being 1. Now there's two types of problems that they're going to ask you. One, they want the net area, the net positive area. So that net area would be the integral from 0 to 3 of f of x dx, which is 1. The other type of question would be, I want the sum of all the areas. So this is 1, this is 1, this is 1. The fact this is negative, we want to add all three areas up. So it would be 1 plus 1 plus 1 is 3. So you need to make sure which way they want it, if they're asking for the net area, which would be 1, or the total area, which would be 3. So, that's it. Now, one more piece of introductory information before we actually get into working out a problem. Yesterday I gave you 3 of these, but we have a 4th one, and I want to make sure that you understand this concept. These are summation formulas to memorize. Let me say that again. Summation formulas to memorize. Now, if you do not memorize them, things could go badly for you. So we don't want to have that happen. So, the summation from I equals 1 to n of 1 equals n. That's just saying 1 plus 1 plus 1 plus 1 n times, that will equal n. Now, summation from I equals 1 to n of I, which is going to be 1 plus 2 plus 3 plus 4 plus 5 up to n, is going to be n times n plus 1 over 2, which means the top value times 1 more than the top value divided by 2. Now, summation from I equals 1 to n of I squared. That's going to be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And that's going to end up being the top value times 1 more than it times 1 more than double it divided by 6. And the summation from I equals 1 to n of I cubed is 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed up to n cubed, which is going to be your top number times 1 more than n divided by 2 and squared. So it's basically this term here squared. So those are going to be highly important for you to understand. So, cruising onward. Let's take a function here, and my function, you can see it here, but I'll actually write it in right up here. So f of x equals x cubed minus 3x squared plus 2x plus 4. That's my function. Now we're going to go through calculating the area 4 different ways. We're going to do left-handed rectangles, right-handed rectangles, midpoint rectangles, and finally Riemann sum rectangles. So let's first do 4 left-handed rectangles. So I'm going to get rid of that and put in my 4 left-handed rectangles. So notice we're going from 0 to 2 of this function. So that means my first rectangle, being left-handed, will be f of 0 high. Then my second one would be f of 1/2 high. Then f of 1 high, and then f of 1.5, 1.5 high. And the width is going to be b minus a over n, which is 2 minus 0 is 2. Divide by the number of rectangles, 4. So we're spanning 2, and we have 4 rectangles, so 2/4 is 1/2 width. So our left-handed rectangles are going to be, rats. Okay, we'll edit that out. Okay, back to the wrench. Now our left-handed rectangles, L sub 4, are going to equal, like I said, the width is going to be 1/2 times what? Well, f of 0 plus f of 1/2 plus f of 1 plus f of 1.5. There's your width, or your base, times each height. And so this is going to equal 1/2 times, now when I plug in 0 into my function, I get 4. When I plug 1/2 into my function, I get 4.375, which is 4 3/8 of course. And then when I plug in 1, I get 4 again, and when I plug in 1.5, I get 3.625, which is 3 5/8. Now when I distribute my half to all these and add it up, then I end up with, let's just go like this, L sub 4 equals 8. Okay, now let's do 4 right-handed rectangles. All right, now, notice with the right-handed rectangles, and we'll just do this, R sub 4 equals, once again, each rectangle is 1/2 wide. And now, this time, the right-handed rectangles, my first rectangle is going to be f of 1/2. Then f of 1, then f of 3/2, and then f of 2. See, my final right rectangle is f of 2. So, this is going to equal 1/2 times f of 1/2, which is 4.375, plus f of 1, which is 4, plus f of 3/2, which is 3.625, plus f of 2, which equals 4 again. So R sub 4 equals 8 once again. Wait a minute. Oh yeah, 8, because it's 16 times 1/2. Okay, that's good. All right, now, the third type of area approximation that we're doing is the midpoint approximation. So let's just get rid of this whole thing. Actually, I'll just get rid of this. Okay, so now the midpoint approximation . Okay, let's look at midpoint rectangles now. Okay, now notice the first rectangle has the height at the midpoint between 0 and 1/2. That's 1/4. And then the second midpoint is going to be between 1/2 and 1, which is 3/4. Third midpoint is 5/4, and then the fourth midpoint is 7/4. So, my midpoint calculation, each rectangle is once again 1/2 wide, and then it's going to be times f of 1/2 plus f of, no, not 1/2, what am I talking about? F of 1/4 plus f of 3/4 plus f of 5/4 plus f of 7/4. There's my midpoint calculation. So, that's going to equal 1/2 times, okay, now these numbers are a little bit bigger. When you're putting in 1/4 into that function, you're going to end up with 4.328125. Oops, rats. Plus, now I put in 3/4 and I end up with 4.234375. Then I put in 5/4 and I end up with 3.765625. Then I put in 7/4 and I end up with 3.671875. So, the midpoint of 4 happens to also equal 8. So why is the left, the right, and the midpoint all exactly 8? Well, let's look at all three of those again. Notice the left rectangles, when the function is going up, a left-handed rectangle is going to be an underestimate. But when it's coming down, the left-handed rectangle is an overestimate. Notice this function goes up, down, down, back up again. Up, down, down, back up again, almost like a sine wave. And so you see that we've got underestimate, overestimate, overestimate, underestimate. Now, when I go to the right-handed rectangles, it's the other way around. With a right-handed rectangle, when the function is increasing, it's an overestimate. When the function is decreasing, it's an underestimate. So the fact that this function is symmetrical about the line y equals 4, it basically goes up and down the same amount from y equals 4. So the left and the right-handed rectangles are equal because their errors cancel each other out. And same thing with the midpoint. Midpoint is slightly high, slightly low, then slightly low, slightly high, slightly low, slightly high, slightly high, slightly low. So the midpoint also, all three of these end up being 8 exactly. All right, now, the last one that we're interested in, and this is maximum juice. The exact integral. Okay, now, there's no homework problem that you have that's as involved as this function that I'm giving you. So I'm giving you something in lecture that's completely way more difficult than anything you'll ever have to do. So, follow through. If you can master this, you can do anything. So let's do this thing. All right, so we've got, now let's go with blue here. So we have the integral from 0 to 2 of x cubed minus 3x squared plus 2x plus 4 dx. Never forget the dx. You always need to have that on there because otherwise you don't have an integral. Okay, now by Riemann sums we said that this equals infinitely many rectangles. So the limit as n approaches infinity of the sum from I equals 1 to n of my function, and that means each height of each rectangle times the width of each rectangle. Now, next thing we know is that, we'll put this in red, delta x equals b minus a over n. So it equals the span on the x-axis that we're encompassing divided by the number of rectangles. That's going to be the width of each rectangle. Now in our case, we're going from 0 to 2, so it's 2 minus 0 divided by n, which equals 2 over n. So what that's saying is each rectangle is 2 over n wide. Now, x sub o, then, let's see, how do I do this? Yeah, let's do it like this. X sub I, any given x value is going to equal your left-hand limit, whatever that is, in this case it's 0, but we'll just call it A as a left-hand limit, plus the width of any given rectangle times I. Okay, that's always going to be the case, that any given x value that I want is going to be the left endpoint of the interval plus the width of each rectangle times the counting number, I. Okay, so that means our x sub I, in this case, is going to be 0 plus 2n over I. Or 2 over n times I. Okay, that's our x sub I. So now what that means is x sub 0 equals 0. X sub 1 equals 2 over n. X sub 2 equals 4 over n. X sub 3 is 6 over n. X sub 4 is 8 over n. X sub I is 2i over n, or 2 over n times I. All right, cruising onward. We now have the parts that we need to evaluate our Riemann sums. So this is going to equal the limit, as n approaches infinity, of the summation from I equals 1 to n of f of x sub I delta x. Now we have delta x set, so let's just put the delta x in there now. So delta x is 2 over n. Now, f of x sub I is going to be the function with x sub I put into it. Well, what's x sub I? It's 2n over I, or 2 over n times I. So that means we have to go x cubed is 2 over n times I cubed minus 3x squared, which is 2 over n times I squared, plus 2x, which is 2 over n times I, plus 4. And this is all times the dx, or the delta x, which is 2 over n. Now, another thing that we can do here, or basically let me put it like this. Our goal is to get all the n's to the left of the summation. So, since there's no I in 2 over n, then I can move that to the left here. So I can make this the limit as n approaches infinity of 2 over n times the summation, we'll just do it like this, summation from I equals 1 to n of, now let's just go through all this stuff. So we've got 2 over n times I cubed, so that's 8 over n cubed times I cubed, minus this is going to be 4 over n squared times I squared, so 4 times 3 is 12 over n squared times I squared. Now we have 4 over n times I, and here we have plus 4. Okay, now, like I said, the goal is to get the n's over to the other side. So what we're going to do is we'll just put this as 4 separate summations. So what we're going to have is the limit as n approaches infinity of this first chunk. Well, what do we have here? 2 times 8, which is 16, over n times n cubed, which is n to the fourth, times the summation from I equals 1 to n of I cubed. And let's just make one limit here on this whole thing. So we've got the limit. Notice this first chunk is 16 over n to the fourth times summation from I equals 1 to n of I cubed. Now, what's next? 2 times 12 is going to be a minus 24 over n cubed times the summation from I equals 1 to n of I squared. And you know what we're going to do, just so you see what's going on here? Okay, so cruising onward, we have 2 times 4 is 8 over n squared times the summation from I equals 1 to n of I. And then we've got plus 4 times 2 over n, which is 8 over n, times summation from I equals 1 to n of just 1. Okay, so now it's time to plug in the values for each of these summations that you've already memorized. So we've got the limit as n approaches infinity of this first term. So we've got 16 over n to the fourth times actually, let's do it like this. We're going to do the limit all at once. And now this thing is n times n plus 1 all over 2 squared. Okay, so now we have minus 24 over n cubed times summation from I equals 1 to n of I squared, which is going to be n times n plus 1 times 2n plus 1, over 6. Now we've got plus 8 over n squared times the summation from I equals 1 to n of I, which you know is n times n plus 1 over 2. And then we've got 8 over n times the summation from I equals 1 to n of 1, which just ends up equaling n. Okay, so the final result then, what we're going to do is we're going to simplify all these red polynomials. So we've got the limit as n approaches infinity of, now 16 over 2 is 8 times, now the n times n plus 1 quantity squared is going to be n to the fourth plus 2n cubed plus n squared, all divided by n to the fourth. There's my n to the fourth on the bottom. So all I did was distribute all that, and I got that. So now, 24 over 6 is 4, and what do I have here? Well, when I distribute all that out, I'm going to have 2n cubed plus 3n squared plus n, all divided by n cubed. Now, 8 over 2 is 4, and n times n plus 1 is going to be n squared plus n, all divided by n squared. And then 8 over n times n is just 8. All right, now, what I'm going to do is I'm going to break these up into separate pieces. So this is going to equal the limit as n approaches infinity of 8 times. Now, notice n to the fourth over n to the fourth is 1. 2n cubed over n to the fourth is 2 over n. N squared over n to the fourth is 1 over n squared. Now I've got minus 4 times 2n cubed over n cubed is 2. 3n squared over n cubed is 3 over n. 1 over n cubed is 1 over n cubed. Now, I've got the 4 times n squared over n squared is 1, plus n over n squared, which is 1 over n, plus my 8. Okay, now, when we let n approach infinity, 2 over infinity is nothing. 1 over infinity squared, nothing. 3 over infinity, nothing. 1 over infinity cubed, nothing. 1 over infinity, nothing. So, what do we have here? We have, let's put this up here, the integral from 0 to 2 of x cubed minus 3x squared plus 2x plus 4 dx equals 8 times 1 minus 4 times 2 plus 4 times 1 no way, something has gone awry. Oh, rats! I made the same mistake again. Made that mistake before when I was working this out. Notice, this is 16 over 2 squared. So this is not an 8. This is a 4. This is not 16 over 2, it's 16 over 4, which is 4. So we have, back to the ranch. So we have 4 times 1, which is 4, minus 4 times 2, which is 8, plus 4 times 1, which is 4, plus 8. So 4 minus 8, negative 4, plus 4 is 0, plus 8 is 8. So this is a unique situation where your right-hand approximation is 8, your left-hand approximation is 8, your midpoint approximation is 8, and the exact value of the area under the curve is 8. So this is it. Now let me just go over the basic strategy with you. And I would advise going back over this again, make sure you know how to do this, because this is going to be really important. You might walk in sometime and there could be a quiz! Or even more important than that, this could be on the test! So, be ready. Okay, so now what are we doing here? Well, first thing we have is the limit as n approaches infinity of a summation. So you have to get your delta x. When you get your delta x, then you can get your x sub I. Once you get your x sub I, then you can get your f of x sub I. Now the f of x sub I was big because we have 4 different terms in the function. But normally it won't be that huge. But the next thing is then, we've got n values and we've got I values. And the key thing is when we can get to the point where the I values turn into n values. Notice the summation of the i's all have shortcuts, which are n's. Now, the n's then cancel with the other n's that you have from your delta x and your f of x of i's, and those are going to give you a final result of a single number. Because, what are we doing here? We're getting the area under a curve, so the answer will always be a numeric value. Okay, that's it. Have fun with these.